We currently understand that our reality is deeply connected to scientific concepts, and while science fiction films and perhaps even religious texts highlight apocalyptic themes, imagine if we told you that the end of the universe could mirror its beginning. The James Webb Space Telescope has revealed that the universe has ceased expanding, a prediction that renowned scientist Brian Cox made years ago. This gives us a compelling starting point to envision an apocalypse. We can trace this journey back to a time before galaxies existed, marked by the oldest light in the universe. So, if some people doubt the Big Bang Theory, the evidence is right before our eyes. We may be heading toward a Big Bang 2.0. Join us as we explore why the universe has stopped expanding and the unsettling discoveries made by the James Webb Telescope. If we are certain of anything in our understanding of the universe and its history, it's that our epoch of existence revolves around an event known as the Big Bang. Of course, there are alternative theories that describe the universe's beginning, such as eternal inflation or a cyclic universe, but we won't delve into the validity of those theories today. Instead, it's important to note that the scientific community broadly accepts that our universe's history begins with a Big Bang. The concepts that follow this event also relate to the same fundamental moment of the universe's birth. While Big Bang is a common term in the theoretical astrophysics lexicon, our understanding of the mechanics behind it remains limited, unless you're a dedicated enthusiast who has spent hours studying detailed simulations. Essentially, the Big Bang refers to an event originating from an incredibly hot and dense point, which expanded rapidly. At this point, the universe was extraordinarily young. In fact, it was only 10 to the power of negative 34 seconds old, about 100th of a billionth of a trillionth of a second. This was when the universe underwent an extraordinary expansion, also known as inflation. During this inflation, space expanded faster than the speed of light. In less than a blink, the universe increased in size many times over, going from subatomic scales to the size of a golf ball in just 1 second. Following this rapid expansion, the universe began to cool, leading to the formation of matter as we know it today. Remarkably, by 1 second after the Big Bang, the universe was filled with all the fundamental particles we learn about in science class: protons, neutrons, electrons, positrons, photons, and neutrinos. While this may sound like science fiction, it reflects our theoretical understanding of the universe's origin. Since the first moon landing, our technological advancements have been profound, and scientists studying the Big Bang relied on mathematical models and theories, with no way to visualize such an event in real time. However, significant strides have been made in our quest to study the universe, yet even today, our technological limitations prevent us from replicating the Big Bang or traveling back to observe it directly. Our most significant evidence comes from the cosmic microwave background radiation, which allows scientists to observe the afterglow of the Big Bang. This tool has been revolutionary in the study of the universe, but it also has its limitations. One major challenge is that we can only observe gravitational waves and residual radiation from the initial expansion. While we have a substantial amount of data about the Big Bang, much of it is theoretical and open to interpretation. Despite our confidence in the Big Bang Theory and its pivotal role in shaping our universe, some aspects of the fallout remain misunderstood. As surprising as it may seem, theories about our universe rely heavily on information that is subject to human error. Our understanding of the Big Bang, while comprehensive, cannot be considered absolute. Is our universe still expanding? In recent years, the Hubble Space Telescope was our primary tool for exploring the universe's expansion, but now we turn to the advanced capabilities of the James Webb Space Telescope. One of the biggest debates in astrophysics was whether the universe is indeed expanding. If you were to read a science textbook from the mid-1990s, you would find discussions about the expansion of the universe. However, a troubling realization has emerged. We might not fully understand what this expansion entails. The James Webb Space Telescope has delivered some startling insights. It seems that the universe has stopped expanding. Before we dive into the implications of this significant shift in our understanding of the universe, let's first clarify our grasp of this extraordinary phenomenon. The most common portrayal of the Big Bang in popular culture depicts it as an explosion, often infused with vivid imagery. Movies and media often illustrate the universe's beginning as a cataclysmic event that disperses energy and matter in all directions. However, scientifically speaking, this perspective is misleading. The universe did not expand into space. Rather, space itself came into existence with a Big Bang. It's more accurate to view the Big Bang as the simultaneous emergence of space throughout the universe. Our understanding of this phenomenon also indicates that our universe has gone through a long, stable period, interrupted only by the reuniting of space. Prior to this event, the universe was completely dark and cold. The moment when light first illuminated the universe occurred about 400 million years after the Big Bang. Indeed, the Big Bang only generated the fundamental components necessary for the creation of living beings and celestial bodies. For 400 million years, the universe remained devoid of light. The creation of the Hubble Space Telescope revolutionized our understanding of the universe. It was instrumental in studying distant supernovae, which helped scientists explain the uniformity of space. By observing these supernovae, researchers gained insights into the expansion of the universe. However, what they discovered was radically different from previous beliefs, leaving them utterly astonished. The revelations prompted a fundamental shift in cosmic research, necessitating a re-evaluation of theoretical frameworks based on Hubble's findings. For the first time, researchers could see the universe expanding not just at a steady rate, but at an accelerating pace. Surprisingly, gravity was not slowing down this expansion, contrary to what was previously thought. Instead, it became clear that the universe was expanding faster than ever since its inception. This new understanding challenged existing theories, as gravity was expected to counteract the expansion, not facilitate it. To this day, the reasons behind this rapid acceleration remain a mystery. Initially, scientists speculated that some unknown force was overpowering gravity, enabling this accelerated expansion. Before the arrival of the James Webb Space Telescope, the prevailing view among researchers was that the universe was a battleground of forces. Following Hubble's findings, the scientific community was thrown into disarray, with organizations like NASA scrambling for explanations regarding this unexpected cosmic acceleration. One hypothesis suggested that Einstein's theories on gravity might be less accurate than previously believed. Einstein had described gravity as a warping of spacetime caused by mass and energy, which would imply that the universe shouldn't be expanding at an accelerated rate. Other theories proposed the existence of a mysterious energy field that could drive this expansion. Despite numerous theories, none seemed to hold firm. Ultimately, the leading explanation for Hubble's astonishing revelation can be encapsulated in two words: dark energy. This term is crucial in modern science, yet remarkably, we still know very little about it. Current understanding suggests that dark energy makes up most of the universe, about 70%, while ordinary matter accounts for only about 5%. This aligns with Einstein's cosmological constant, which posited that even in empty space, there exists a form of energy that remains constant and unyielding as the universe expands. But how does this relate to the observations made by the James Webb Space Telescope? Why has the universe seemingly ceased its expansion in the presence of dark energy? Scientists are still grappling with these perplexing discoveries. If we examine the dynamics between gravity and dark energy, we might find clues. The cosmological constant is often considered a proxy for dark energy, suggesting an ongoing struggle between gravity and dark energy. In earlier stages, it appeared that dark energy was outpacing gravitational forces, allowing the universe to expand at an accelerating rate. Now, however, this phenomenon seems to have stopped completely. Given our limited understanding of space and dark matter, researchers are at a loss to explain this sudden halt. Some speculate that gravity is finally overpowering dark energy, bringing the expansion of the universe to a standstill. If that were the case, the universe would likely have contracted significantly before the expansion completely halted. Alternatively, it might be that gravity has suddenly begun to diminish the effects of dark energy. In summary, the Hubble Space Telescope's revelations forced a complete reassessment of our understanding of cosmic expansion, and the interplay between gravity and dark energy continues to puzzle scientists as they seek to unravel the mysteries of our universe. The universe once plunged into obscurity. For a long time, there were no stars or planets. This changed when clouds of gas began to coalesce into stars and galaxies, marking the end of an era of darkness. Interestingly, our solar system formed about 9 billion years after the Big Bang, a significant delay after the universe had spent approximately 400 million years in darkness. It's essential to clarify a misconception popularized by science fiction films. There is a vast gap between the Big Bang and the formation of our solar system. The prevailing view is that the universe originated from a singular point and has not remained static. Rather, it has been expanding over time. This expansion doesn't mean the universe itself is moving in a conventional sense. Instead, it is the fabric of space that is stretching, carrying matter along with it. This can be a complex concept to grasp, but understanding the implications of it is vital. For this discussion, we will refer to the universe's expansion as the dynamic growth of space. This terminology is commonly accepted among scientists and has been supported by findings from the James Webb Space Telescope, which recently revealed that the universe's expansion has ceased. This revelation is both surprising and contradictory to previous scientific theories, which suggested that the universe had been expanding at an accelerated rate since its inception. Before this groundbreaking discovery, scientists, aided by the Hubble Space Telescope, had gathered substantial evidence supporting the idea of an expanding universe. This isn't a case of NASA correcting its previous understanding. Rather, it highlights that whatever is happening to the universe now is entirely new and possibly irreversible. Despite the startling nature of this discovery, it is not entirely unexpected. Discussions around gravity indicate that the universe has always been susceptible to the potential of collapse. If there is enough energy density, expansion could theoretically halt entirely. In the 1990s, NASA and its researchers had compelling theories about the universe's expansion, with gravity being a central component of their understanding. Although this fundamental concept remains valid, our current theories about the universe's expansion rates have evolved significantly since then. Researchers once anticipated a potential recollapse of the universe that would halt its expansion, a concept that was equally troubling. They postulated that if the energy density was too low, the universe would continue to expand indefinitely. At that time, researchers had limited technological means to gather substantial observational data to support their hypotheses. They were confident that, as the universe aged, gravitational forces would slow its expansion, an intuitive idea, as gravity pulls celestial bodies together. This led scientists to conclude that, as the universe expanded, the gravitational force would counteract the increasing distances between galaxies. They extended this hypothesis to understand the rate of expansion, believing gravity would act as a limiting factor for all matter, a force that has existed since the universe began. Consequently, they expected that the rate of expansion would have to slow down. However, they had no way to test these predictions with substantial observational data, and this reasoning seemed sound until it didn't. Until 1998, when new evidence began to challenge these long-held beliefs.